So in this video we will look at chapter number 3, which is the Laplace transform circuit analysis. So the content of the chapters are resistor, capacitor, inductor, terminal IV relationship in the S domain. So we will look at the RLC circuit in time domain, and then how can we convert the circuit into S domain or frequency domain. Then we will look at the Kirchhoff voltage and current law in the S domain to perform the analysis of the circuit in S domain. Also, we'll look at the branch analysis, mesh analysis, and nodal analysis in the S domain. And then finally, we can inverse the circuit back into time domain to get the voltage or current in time domain. So now that we have introduced the Laplace transform, let us see what we can do with it. Right? So initially in chapter 2, we learn how to do Laplace transformation using the Laplace transformation table. Now, what can we do with it? Right? This is where we are going to apply the Laplace transformation in circuit analysis. So please keep in mind that with the Laplace transform, we actually have one of the most powerful mathematical tools for analysis, synthesis, and designs, right? So being able to look at circuits and systems in the S domain can help us to understand how the circuits and system really function, right? In this chapter, we will take an in-depth look at how easy it is actually to work with the circuit when we convert or transform the circuit in the S domain. So let's look at the RLC circuit. So first we look at the resistive network transformation. Let's look at the R component, resistive component. So we have here, so you can see here we have the so we have the resistor. Right, this is the resistor in time domain. Right, this is in time domain. Right, so we see here, we can see here that the resistor has current flowing through the resistor, right, which is IRT, and then we have voltage across the resistor, okay, which is the VRT, right? T stands for time domain. Now, so here the voltage across the resistor is simply equals to resistor, the R times IR. Okay, the current flows through the resistor. All right, or I equals V over R. So this is basic, right? Basic Ohm's law. Now we can also transform this circuit here, right, into frequency domain or S domain, right? So instead of VRT, okay, V in a small letter, so in S domain, V is capital letter, all right, VRS, and then the resistor is still the same, R, and then the current is I, capital I, R, S, all right, and the equation is similar, VIR, I equals V over R, I equals V over R. So for resistor, it is basically similar, right, between time domain and frequency domain. It's the same. Now let's look at inductive network transformation. Let's look at the resistive, inductive. All right, so in inductor, okay, same thing. So we have inductor here, L, and then we have the voltage across the inductor, which is VL, and then we have the current of the inductor, which is IL. Now, in time domain, the voltage across the inductor is represented by the L di over dt. Okay, L times dIL over dt. All right, and then IL, the current of the inductor equals I over L integration of voltage across the inductor. So this is in time domain. However, if we convert or transform this circuit VL and I in S domain, right, we can see that the value has changed. Okay, the first thing we can see is the L itself, the inductor itself. So here inductor is L, right? But in frequency domain, in S domain, the inductor is now S times L, or SL. All right, so now the inductor itself is SL, and then V is still the same, VL, IL, but the equation is different. Right, the equation is different. As we can see here, the VL, okay, voltage across inductor, is now SL times I minus L times IL. Okay, but the IL is this is the initial condition, right? This is actually the source, voltage source, additional voltage source. All right, so basically we have additional component in the circuit. If we convert L, inductor, from time domain into frequency domain, we can see that here we have additional component in the circuit. So this is the initial condition, all right, represented by a voltage source. Now take note on the direction or the polarity of the voltage source. This is important because some students, they will do a small mistake. So you can see here the direction of the current. If the direction of the current is this direction, then the polarity is plus minus this direction as well, right? It must follow the same direction of the current. So now we can see that the voltage across the inductor is now quite similar to V equals IR, right? So V is the voltage, I is the current, R or Z impedance is the SL. So this is the inductor SL now. So instead of having to L times di over dt or integration of VL against dt, now it's simply just multiplication of SL times L. Okay, same thing for the current. You can see here in the current, for the current, simply V over LS, and of course not to forget the initial condition, which is IL over S. All right, so so here you can see here this is the same thing, right? We have the circuit in time domain, and then we convert into S domain, and also the circuit in S domain, if the source is now in parallel. All right, see here, this the inductor and the voltage source or the initial condition is in series, but in this case the inductor and the source is now, or the initial condition is now represented as current, and it is now in parallel. Both are similar. Okay, so both are similar. You can either use this or use this, all right, to suit your to suit the circuit, so that certain circuit it is easier to solve if you have these two components in series. On certain circuits, it is easier to solve if you have the components in parallel. All right, but both are similar, both are interchangeable. All right, and regarding the initial condition, this is important. IL 0 minus, okay, this is actually the current of the inductor slightly just before 0 second. Okay, 0 stands for the time at 0. All right, or in other words, the inductor of the current at 0. All right, pretty much at 0. So we are going to analyze the circuit after 0, from 0 and above, right, after that. But we need to know if the inductor has current at 0, because we have to consider that as initial condition in the analysis. All right, so usually in example or in questions, initial condition will be given. All right, so if the initial condition is not given, it's not provided, then you can simply assume IL is equals to 0. All right, next is the all right, so basically it's the same thing, right? Now let's go to the final one, capacitive network transformation. All right, so you can see here that the capacitor, we have current flowing through the capacitor ICT, we have the voltage across the capacitor VCT, and the capacitor itself C. All right, this is in time domain, and then so you can get the current of the capacitor equals to C dV over dt, or you can get the voltage of the capacitor using this equation, 1 over C integration of IC dt. Right, and if you can see here, this is slightly reverse to the inductor. All right, now let's look at the frequency domain. Right, so in frequency domain, same as in inductor, we have to consider the initial condition, all right, of the capacitor. If the question or examples provided the initial condition, then we have to consider that in the equation or in the analysis. If the initial condition is not given, then we can simply assume it is 0. All right, so here we can see that the capacitor in frequency domain is 1 over SC. Okay, 1 over SC. All right, so it is different compared to inductor, in which for inductor the value is SL. Okay, L in time domain, but SL in frequency domain. C in time domain, but 1 over SC in frequency domain. All right, then for the current, before that, the the initial condition is represented as a voltage supply or voltage source, right? So here the voltage source is represented as Vc over S, right? Vc over S. So if there is no initial condition, then you can just simply consider this as zero, short circuit, right? So IC, you can simply calculate it as SC times VC. Okay, so I equals V over Z, right? So Z in this case is 1 over SC, so therefore the SC itself is bring it to the denominator, right? So here is actually VC 1 over SC, right? Now you can bring SC to the top, so that it is now SC times VC. And then of course don't forget the initial condition. Okay, so same thing for voltage of the capacitor. V equals I Z, and then in this case Z is 1 over SC. Alright, so 1 I equals I over SC. Alright, so now you can see that the equation, voltage and current equation of the capacitor and inductor are now much easier to calculate, all right, because they are just a simple algebraic calculation instead of d over dt or integration of dt, right? And same thing for capacitor. You can represent the initial condition as voltage source and take note on the polarity, and also you can represent the voltage source as in current source, but it is now in parallel with the capacitor. Okay, so basically as you can see here that this is the inductor, right? And this is the inductor in S domain with voltage source representing the initial condition of the inductor. And if you perform source conversion, or you convert the source from voltage to current, right, then you can represent it as I over S. Same thing for capacitor. The initial condition is represented as voltage source, but take note on the polarity. The polarity is different with the inductor, right? And if you perform source conversion, you can represent the initial condition as a current source, but it is must be in parallel with the capacitor, right?